Principles of Bioproduct Separation Module 9 Illusion Chromatography Segment 5 Scaling Up Chromatography. With me, Yusuf from School of Life Sciences and Technology, Institut Teknologi Bandung. Previously, we have discussed bioabsorbance, yield and purity, discrete stage analysis, and kinetic analysis. In this segment, we will discuss about scaling up chromatography. At the larger scale, we want a bigger capacity, but with the same yield and purity. A bigger capacity means a larger throughput. The easiest way to increase the capacity is to increase the solute concentration in the feed. Such an increase often saturates the packing and reduces the purification. As a result, larger scale chromatography cannot be achieved by increasing the solute concentration. A more effective way to increase the capacity while maintaining purification is to increase the flow of the column. Maintaining the purification requires that the concentration profiles of each solute cannot be dramatically altered, which can be expressed by equation 38. Thus, the concentration Y is a function of three parameters: Y0, V per V0, and sigma. If these three parameters are unchanged, the concentration profile will be unchanged. The maximum concentration Y0 is largely fixed by the inlet concentration. The ratio of volume V per V0, or alternatively the ratio of times, is easily kept constant. If the bed is twice as long, the velocity in the bed is just twice as fast. Standard deviation is the key in scaling up chromatography, which can be calculated by using equation 39. In particular, the area per volume A for a packed bed of spherical particles is given by equation 40. The variation of rate constant K depends on the step which controls the interactions of solute and packing. If the step involves diffusion and fast reaction within the particles, then K is independent of the velocity outside the particles and can be calculated using equation 41. If the controlling step is mass transfer between the bulk and the particle, K increases with increasing velocity but decreases with increasing particle size as shown in equation 42. The standard deviation for both cases can be calculated using equation 43 and equation 44. In both cases, increases in velocity and the particle size increases sigma and hence increase the width of the pulse. The standard deviation may also change because of dispersion. The exact relation between sigma and the dispersion depends on the flow in the column. Some of this dispersion comes from polydispersed column packing, and more can come from the nature of the flow itself. Standard deviation for laminar and turbulent flow can be calculated by using equation 45 and equation 46. Scaling up the separation, the variation of the standard deviation with conditions in the column can be summarized as shown in the table. One choice is to keep the ratio of the packing diameter to column diameter constant. This choice will preserve the character of the flow in the packed bed, yet will allow us to use larger, cheaper packing. As a second choice, we fix diameter and increase both V and L at constant V per L. This works reasonably well for all the rate controlling steps, but will cause a large pressure drop and can deform the packing and hence effectively plug the bed. The solution is to use short fed columns. Such columns should have similar values as those used in the small-scale operation. Their increased capacity is due to the greater cross-sectional area. For the next segment, we will do several exercises. Until then, I am Yusuf from Institut Teknologi Bandung.